The aluminum casting industry plays a major role in the automotive and aerospace markets. It is witnessing considerable growth due to advancement in technology and rising demand from the transportation sector. The electric vehicle market, in particular, is driving demand for high-strength, lightweight materials that can replace traditional steel. But this trend faces major challenges. Part manufacturers are expected to produce more parts at lower cost, while meeting higher quality requirements. Safety concerns and increasingly complex design make part inspection more demanding, while specialized labor shortages add pressure on part manufacturers. Casting imperfections are unavoidable as they are inherent to a complex process very difficult to master. X-ray technology is the preferred inspection method for castings since it can see these imperfections. X-ray has been around for more than 100 years. In recent years, digital technology has significantly improved industrial X-ray capabilities, but despite the introduction of more advanced technology, inspection methods have remained essentially the same. Radiography is still considered to be a labor-intensive and a very costly inspection process. There's got to be a better way. This is where predictive 3D radiography comes into play. Predictive 3D radiography is our patented technology that combines X-ray physics with 3D analysis, simulation, and artificial intelligence. It fully exploits all the available information to provide unique automated capabilities that are efficient, very fast, tailored to client needs, and much less expensive than traditional methods. Based on inspection standards and business rules, it delivers comprehensive results that can easily be interpreted by the end user or drive a fully automated inspection process. With predictive 3D radiography, 100% inspection is now possible and cost-effective, even for high-speed inline applications. What's making all this possible is LynX Studio, the very first software development kit designed specifically for high-performance industrial X-ray inspection applications. LynX Studio is a computer vision library with all the individual software modules needed to build custom X-ray applications that are modular, vendor-agnostic, highly scalable, and that take full advantage of the parallel processing power of GPUs. The framework in LynX Studio uses stateless programming principles, where each component is available through an object-oriented data structure. Individual modules are called programs that can be configured and executed independently from each other or in a predefined sequence. Programs are attached to stations that connect to devices before execution. Each device can easily be configured through a set of parameters. Programs can be executed from within the framework, from a dedicated GUI, through command lines, or even a web interface. The same program can be executed more than once, and multiple programs can be run simultaneously. One of the key features of our SDK is a real-time X-ray simulator. The simulator can be used to provide a digital representation of the real-world conditions, also known as a digital twin. A digital twin can be used to validate scanning parameters, find optimal viewing angles, or test the individual steps of a workflow sequence, for example. But simulation is also used in other areas, such as helping with image registration and 3D positioning, performing scaling assessment, finding anomalies against a reference model, and even building multiple test cases to optimize deep learning model training. But the best way to demonstrate the real power of the SDK is to show a real-life example. The following demonstration shows how a sequence of events are being used to generate automated defect detection results. Taking a sample aluminum casting, the program starts by positioning the part in the cabinet to acquire an X-ray image. It then cleans the resulting image based on calibration data, then performs a registration of this image in 3D space and generates the corresponding 2D projection and scaling map that can be used for grading. Finally, it finds all the individual indications using the deep learning AI model and grades the overall part by assessing these indications against the reference standard and business rules. First, we place the part inside the cabinet and close the door. We're now ready for scanning. Then we activate the program. The part moves into position. X-ray is turned on and the image is acquired. From there, all the processing steps take place in just a few seconds. Total elapsed time between X-ray on and grading results is around 14 seconds. All the intermediate results are available for review. These include the segmentation results, the simulated image, the magnification map, the projected regions of interest, and of course, the overall grading results. As we can see, some of the indications exceed the acceptance criteria and show up in red, while other indications are acceptable and remain in green. Note that this program will work even if the part is tilted and rotated. Let's demonstrate this through another scan. As we can see, the new results reflect the new position of the part. And the 3D scene gets updated with the tilt angle that was detected by the program. This is only an overview of what this framework allows us to do. We can use the same tools to support more advanced inspection solutions, such as 3D defect positioning using multi-view imagery, or fully automated inline inspection solution using multiple sensors capable of surface and subsurface defect detection.